Hey kids, ready? Here we go. Section 6.3, volumes by cylindrical shells. Hopefully you've gotten through 6.2 and saw that we have the method of discs and washers to find volumes. We're going to now see that there is yet another way that we can find volumes by rotating a curve about an axis of rotation. So let's consider the function y equals x minus 1 times x minus 3 squared. So I have that graphed here for you. Right, and we're going to look between the values of 1 and 3 right here. So in the area bounded by the curve in the x-axis. Okay, so this is a nice area. Remember, when we're looking at area bounded by a curve in horizontal or vertical lines, and we're looking for the volume when we rotate this curve, one of the first things I told you to focus on was the up to down and left to right relationship, or top to bottom and left to right. Notice if we go top to bottom, so here's our curve of interest right here. So this is our top curve right here, and then the bottom would just be the x-axis. Now if we go top to bottom here, top is always the function x minus 1, x minus 3 squared, and the bottom will always be the x-axis. So no matter where I go, top to bottom, we have that same relationship. If I go left to right, we have a little bit of a problem here. So imagine spinning this about the y-axis, and we try to use that left to right relationship that we established with discs and washers. We find that the right curve is the same as the left curve when we look horizontally, and that's going to create an issue because when we do the right minus the left, they're going to cancel each other out. So here, a horizontal rotation would work fine using our washers, but a vertical rotation would create a problem. So how do we settle this? Well, we have this new method we're going to talk about. We want to rotate this solid area about the y-axis, this area, and create the volume, create a solid and obtain the volume. So how do we do that if we can't establish that right to left relationship without things canceling out? Well, what we're going to do here is we're still going to use, even though we're rotating about the y-axis, we're still going to use that top to bottom, and we're going to imagine we're going to cut out one little rectangle like this. So we're going to take this rectangle right here. That's going to represent that area between those 2 points, and we're going to spin that. So if we spin that, imagine the shape, the resulting shape looks like this, right? And then we spun it about the y-axis. So what it's going to create is like a tin can. And our goal is to make these, the widths or the thickness of the tin can, get that infinitely small and then take an infinite collection of these nested tin cans. So this is now the shape of interest. It's called a cylinder or cylindrical shell. And we're going to use these cylindrical shells to find volumes in a different way. So let's talk about the volume of a cylindrical shell for a moment. So notice here we're rotating about the y-axis, and we're gonna go, I'll do it over here because I'll go to the left because I have too much going on. So we sort of have an inner radius, and then we have an outer radius to the outside of the shell, right? And then we have a height of the shell. So what we're going to do is we're going to take this shell, so we have our inner radius and our outer radius. We're going to take this and we're going to cut it with some like little scissors right here. We're going to cut it along that line, and we're going to open it up, and it's going to produce this slab. So this volume of the slab is the same as the volume of this cylindrical shell. We have an outer radius and an inner radius, right? So what I'm going to do is I'm going to call the radius of this thing, I'm going to go right in the middle of the inner, the outer. We'll call that R. We have the height of this guy, H, right? So now let's put that down here onto this picture. Let's transpose it down here. So the height of it will transpose to the width. The thickness right here, right? That thickness is going to be this right here. Right? We're going to call that, let's just call it, I'm going to call it R for now. We're going to call that with R between the inner and the outer radius. Let's call that R, right? And then what would be the length of this thing? So if we cut this can and open this up, well, the length is going to be the distance around the top. Okay. So the distance around the top, well, it's just the circumference of the top of the cylinder. And the circumference is 2 pi times the radius, right? And I'm just going to use the radius as the thickness. Now, I don't know if I want to call that r. You know what I'm going to do? Let's go back here. We're going to call the thickness delta x. Doesn't that make sense in this picture? Because it's the change on the x-axis. So I'm going to call this thickness right here, the thickness of this guy, I'm going to call it delta x instead. So that's going to be this thickness right here. And then I'm just going to use the middle of the outer and inner radius to help me estimate the circumference around the top of the circle. So the volume of the cylinder, it's just now a rectangular slab. So it's 2 pi r times the height h times the thickness delta x. Okay. Now let's look back at this guy. Delta x is going to be the width. Notice the radius of this is from here to here, and that's just whatever value it reaches on the x-axis. So the radius is just x. So we're going to replace r with x. And then the height of the cylinder, well, it depends on this value right here of x. So the height is the function evaluated at x. So we would put whatever the x value is into the function. So this is just f of x. So therefore, when we look at one little cylindrical shell, the volume is 2 pi x f of x delta x. And then we're going to take an infinite collection of these, and we know when we let delta x go to 0 and take this infinite sum, we create integration. That's how integration is formed. So the volume of the solid obtained by revolving a function f of x about the y-axis between x equals a and x equals b using cylindrical shells is found by 2 pi. I'm going to pull the 2 pi out front. We're going to go from a to b. X, I already pulled that 2 pi out, silly, 2 pi f of x dx. F of x dx. So this x represents the radius of the cylindrical shell. F of x is the height. Right, so let's do this. Let's find the volume of the solid obtained by revolving this area under the curve, y equals x minus 1 times x minus 3 squared, about the y-axis. Right, so we would get something like, I should have drawn it, but I didn't. Let's say something like this, right? I'm going to imagine that in like 3 dimensions. It would be something like this. Almost like a sort of a donut-y shape. We want to know that volume. Well, the volume can be found by, how I look at it is I go top to bottom, and I just imagine one cylindrical shell, top to bottom. And here's my cylinder from top to bottom. My x values are ranging from 1 to 3. So I'm going to pull the 2 pi, the constant 2 pi out. I'm going to go 1 to 3. For any shell, the radius is from the axis of rotation to the outside of the shell, and so that would be whatever value that obtains on the x-axis. That's going to be x. And then the height of the shell depends on the x value. So at 2, the height here at 2, we would plug 2 into the equation. The height at 1 would be, at 0 would be 0. So notice if we put 1 in there, we get 0. So the height is just the function itself. So x minus 1 times x minus 3 squared dx. There you go. So you would integrate this. I'll let you do the work in between. This is just multiplying out. So I would distribute and then FOIL and distribute again. And I got 24 pi over 5. So why don't you do this? All right, and make sure that we agree on that answer. All right, so let's try another one. Let's find the volume obtained by revolving 1 over x, the region bounded by 1 over x in the x-axis between 1 and 4 about the y-axis. So this is pretty straightforward again. So, so 1 would be here, and 4 would be here. Right, so we're looking at this region right here. Right. Now notice, again, I'm very thankful that we're revolving this about the y-axis and using shells. If we do a top to bottom relationship, the curve y equals 1 over x is always what's on top, and the x-axis is always what's on the bottom. If we were to go left to right, that relationship changes when we're down here in this little region. So things get a little bit messy if we were to revolve this around the y-axis and use washers. So this cylindrical method is saving us some considerable algebra here. So that's the function y equals 1 over x. We're going between 1 and 4. So according to this template, the volume is going to be 2 pi. My vertical lines, like imagine doing an infinite collection of vertical lines. My vertical lines range from 1 to 4. At any point, like if we were to look at this one right here, and imagine the cylinder obtained by spinning this guy, it would look like this, right? No, it would be over here, and it would sort of look like this, right? And the radius would be from this point to this point, and the length of this line would just be the x-coordinate on the x-axis, so the radius is x. And then the height, we would just plug in whatever this value is into the function, 1 over x, and then we're going to integrate that with respect to x. Look how super easy that is. That's just 2 pi. We're integrating just 1 dx. When you do the math, you get 6 pi. All right, so make sure you can do the work in here. It's just basic integration. Right now, previously we learned how to use discs and washers. So let's see, how would we set this up using discs and washers? And when you see how we would set that up, you're going to appreciate this new method of cylinders. Okay. So let's find the same method. So let's pretend we didn't do cylinders yet. We're going to go from 1 to 4, and we're going to rotate this region right here. Right here, we're going to rotate this region, and we're going to go, if we were to rotate it about the y-axis, we would have to go right to left using the methods from our previous section. So right to left, well, things behave nicely, y equals 1 over x, until we hit this point right here. And then below, from this point down, we have a different right to left relationship. So what we have to do is look at this in 2 pieces. So this is going to be volume 1 and volume 2. So that being said, let's set it up. We're going to have volume 1. Well, this goes from, I'm going to go from, let's see, well, if we put in 4, that's going to be from 0 to 1/4. And then the other one's going to go from 1/4 up to 1. So my first volume 1, was going to be, well, we're going from, we have to now integrate with respect to y because we are doing washers and we are rotating vertically. So my y's go from 0 to 1/4. We pull the pi out front, and then it's my outer radius, which is 4 squared, minus my inner radius, which is 1 squared, dy. Volume 2 would be this. Oh, I switched them. I'm sorry. Let's call this volume. Silly me. I did the easy one first. Let's call that one and that one 2. There we go. So now the upper one, volume 2, is going to be pi. My y's go from 1/4 to 1. The right curve is now y equals 1 over x, but we have to solve for x. We get x is equal to 1 over y. So the radius at any point of one of these guys, oh, nope, wrong thing. Sorry, backpedal. Volume 2, I screwed myself up here and now I'm all disheveled. All right, try again. Volume 2, we are going from 1/4 to 1. It's going to be the outer radius minus the inner radius. So the outer radius depends on y. It's 1 over y. Outer radius squared minus any inner radius is always 1 squared. So it's right minus left and dy. So I challenge you, integrate, add, get, it will still equal 6 pi because no matter which method we use, either cylindrical shells or discs and washers, the volume obtained when we spin this thing, it's going to look like something like this. What's it going to look like? Right, it's going to look like a, I don't know what you want to call it. Or if it's going to have like this little inner tube cut out right here. It's going to look like that. Right, it's going to be this thing. sort of a Christmas tree stand. Yeah, there we go. It's a Christmas tree stand. Okay. So integrate, see if you can get the same result as we did with shells. So let's see if you can follow discs and washers versus cylindrical shells. All right, bear with me here. All right, so let's suppose we have a great top to bottom relationship. So if we have this awesome top to bottom relationship, right? So the top is always the same function and the bottom is always the same function. We always want to integrate top to bottom, right? So now, if we were going to integrate this, if we were going to have to spin this about the x-axis, notice if you spin one of these little lines, it comes down here and it's going to create like a washer, right? So if we have an up to down relationship, a good top to bottom relationship, and we're spinning horizontally, this lends itself to either discs or washers. Discs are just washers without the middle. The air is flush against the axis of rotation. So this lends itself nicely to washers. So the best way I can say this is it's going to be pi. We're going to integrate. If we go up to down, it's always along. We're going to integrate with respect to x because my vertical lines range from A to B. So we're going to integrate from A to B. It's going to be the outer radius squared, or top function squared, minus the bottom function squared with respect to x. So this is, I like putting it, it's a little more general because if our axis of rotation is not an axis, it's another horizontal line other than the x-axis, then we have to keep that in mind. So this is my outer radius squared minus my inner radius squared, okay? All right, if we're spinning it about the y-axis, then when we spin one of these lines, notice we get more of like a tin can that's as thick as the line is. So this lends itself naturally to shells. Okay, and the shells, the volume would be, well, it's 2 pi. My vertical lines range from A to B, right? And the radius, well, if we're spinning it about the y-axis, the radius is just going to be the value of x, and we'll see what happens when it's not the y-axis shortly. So the radius is going to be x. And then the height of one of these guys is the top minus the bottom. So it's going to be f of x minus g of x. So as you can imagine, this can be considerably easier to integrate than squaring functions. So this x in this problem is representing the radius of one of the cylinders, and this is the height of the cylinder. And it's top, always top minus bottom. All right, if we have a right to left scenario where up to down lines don't behave nicely, notice if we go up and down here, then the top curve is the same as the bottom. Funky things start happening over here. But in this, we have a beautiful right to left relationship. So if we have area represented like this, where we have this great right to left relationship where the right curve stays constant and the left curve stays constant, well, depending on if we're rotating horizontally or vertically, we'll use shells or washers. Let's suppose we're going to rotate this one about the x-axis. Well, imagine taking one of these lines and rotating it horizontally. Can you see that we'd get that sort of tin can? I ran out of room down here. Here, I'll do one here, right? And we would get this, something like this, right? So we'd get a tin can. So this lends itself to shells. So the volume would be 2 pi. Now this time we have to go from whatever this value is to whatever this value is. I think I relabeled those C to D for you. So C to D on the y-axis. We integrate with respect to y this time. Because notice my horizontal lines all range from C to D. So horizontally we go C to D. And then we're going to do the radius. So if we're revolving about the x-axis, the radius of this cylinder just depends on the value of y. And then we're going to do the right function minus the left function. But if we were rotating this about the y-axis, let's look at this guy right here, I would have this and I would have a washer right there. So we would do, so if we're rotating, if we have a nice right to left rotation, but we are rotating vertically, that's screaming at us to use washers or discs if it's flush against the axis of rotation. So my volume would just be pi. My horizontal lines range from C to D again, and then I'm going to do the outer radius, so f of y, squared, minus the inner radius, g of y, squared dy. So let's go, this is going to be the outer radius squared. Here we have the inner radius squared. Oh, and I forgot to label this up here. So when we use shells, this y is the radius, right? And this would be the height of one cylinder. And we always do right minus left. There we go. All right. So this just takes lots of practice. All right, let's look at, I'm just gonna, let's see, it says find the volume. I don't know if I found these. I might leave this up to you guys to see. Let's see, find the volume of the solid obtained by revolving the region bounded by f of x equals x squared plus 4. So this is y equals x squared plus 4 because I know it's a parabolic shape, and this is y equals the square root of x plus 4. And here, this is the region. We're going to rotate this about the y-axis. So find the volume of the solid obtained. So let's see, we could do right to left, or we could do top to bottom. Now, because these are functions y expressed as in terms of x, I'm going to stick with the top to bottom relationship here, and I'm going to use cylinders or cylindrical shells. So by shells, well, let's see, we need to know the point of intersection. So we can see that this is the point 1,5. Right, and that's obvious from my graph. If you didn't know that, you would have to set them equal and solve. If you make a good guess, like this looked like the 0.15, make sure you stick 1 in, and when you stick 1 into both equations, the output is 5. So confirm the points of intersection. So the shells would be, the volume obtained by the shells would be 2 pi, and I'm going from 0 to 1. All my little vertical lines would range from 0 to 1. Right? And then the radius of any one of these, because I'm on the x-axis, the length of any of these lines would just be the value of x, so the radius is x. And then the height of the cylinder is the top function, square root of x plus 4, minus the bottom function, x squared plus 4. Now be careful, because it's this whole function minus this whole function. Parentheses aren't necessary in the first one, but because we're subtracting a sum, we have to either include the parentheses or remember to distribute. We're going to integrate with respect to x. Okay, I'm going to let you find that volume. Maybe, maybe you'll see this guy again. Hint, hint. All right. Let's suppose I moved my axis of revolution over here to -2. How does that change things? So what I'm going to do is I'm going to take this right here. This is on top, y equals x squared plus 4. Y equals the square root of x plus 4. Right, and I'm now revolving it about the line x equals 2. So if you can see, instead of having this little shape that's sort of mirror imaged on the y-axis, we're now going to be mirroring -2. So when I go top to bottom, right, I'm going to get something like way over here. So let's see, 1, 2, 3, 4, 5. I have 5 blocks. 1, 2, 3, 4, 5. I'm just kind of drawing it. This, right, so that would be the mirror of that. And this is what one cylinder would look like. Right? All right, so what would this volume be? Let's go with using shells, because I like this top to bottom relationship. I don't have to square anything. The volume is going to be 2 pi, and then imagine drawing an infinite collection of vertical lines. All my vertical lines to stay within that region are going to range between 0 and 1. All right, now the radius, this is where things get a little bit weird. If I look at this cylinder I just drew right here, the radius is from here to here. This is now the radius. It's not just from here to here. So whatever x value this is right here, that x value would just be this little piece, but we have this whole extra 2 units. So this is my radius. And the radius, well, imagine if this is any x value, what would be the length of this line? Well, it would be this x value plus an additional 2. So the radius is going to be, the length of this line is the right value, which is x. That's going to change as that line moves right and left inside that area, but this isn't going to change. It's going to be minus 2. So my radius of my cylinder is going to be x, whatever this is, plus this additional distance of 2. All right? So it's always the right value minus the left value. Always in your radius, you're going to have the axis of rotation. Previously, our axis of rotation was at y equals 0, so it didn't appear inside the radius, but now we've moved it over, so we have this additional length of 2. Now it's going to be the height of this guy. The height is the top function, square root of x plus 4 minus x squared plus 4. And we can integrate with respect to x. All right, I guess I could parentheses around here. So we're going to just clean this up. 2 pi, 0 to 1, x plus 2. It's going to be square root of x minus x squared, because the 4's will cancel out. So I'm going to give that to you as a to-do, and you may see it again, maybe on a future test or something, so that's a hint. So find that volume. Right now I'm going to get this time my axis of rotation was to the first time it was to the left of the shape, and now I just moved it further to the left of the shape. But what happens if I move it over to the right side? How does that change things? All right, we're going to do this same volume right here, same area right here. This is y equals the square root of x plus 4. The top one is y equals x squared plus 4. We are now going to spin it along the line x equals 2. Right, so we're going to have this little shape over here. It's going to flip-flop if I go top to bottom. I can only imagine it's going to look something like this. One of my cylinders are now going to look like this. Right, so that would be one cylinder. I'm going to take an infinite collection of those. My vertical lines will range all between 0 and 1. So using shells, my volume will be 2 pi. I'm going between 0 and 1, right? Now, the radius, think about this. The radius is the length of the line from the axis of rotation to the outside of the tin can. How long is this line? Well, it starts at 2 and it stops wherever that vertical line falls. So if the vertical line fell at 1, it would have a length of 1. If it fell at a half, it would have a length of 1.5. So the length of this vertical line, this is now the radius. Notice the right side never changes, but as we change these little lines inside here, the left side changes. The left side depends on your value of x. So this would be the radius of that one right there. So we always do right minus left. So the radius is now axis of rotation minus the x value to the left. Always right minus left. So this is the radius of one shell. And then the height remains the same. It's the top function, which is the square root of x plus 4 minus the bottom function, x squared plus 4. And then you're going to integrate that all. I know you can do it. This is just power rule. 0 to 1, 2 minus x times the square root of x minus x squared dx. All right, I'd be here for a super long time if we integrated all of these things, okay? All right, let's keep plugging along. Let's set up a couple more. All right, let's look at this cool region bounded by 4 minus x, the square root of 4 minus x, and the square root of 4 minus 4x in the x-axis. So this is my region right here. You can always graph these on your calculator to get an idea what it looks like. All right, so now I'm going to rotate this about the x-axis, but notice I didn't tell you which method to use. So let's decide if a top to bottom or a right to left relationship is better. If I go top to bottom here, and I say, oh, look, the top is, well, let's identify what curve this is. When I stick in 4 for x, which one produces an output of 0? It must be this guy. So this one is f of x equals the square root of 4 minus x. And when I stick in 1 for x, I get 0. So the left one must be the square root of 4 minus 4x. Right there. All right, so I know my right curve and my left curve. If I go top to bottom, I have the square root of 4 minus x, and then we have the x-axis on the bottom, right? And things that happens nicely. But look over here, top to bottom, our top to bottom relationship changed. Way over here to the left of 1, the top curve is f, the bottom curve is g. We move to the right of 1, the top curve is f, and the bottom curve is the x-axis. We don't like that change. We try to avoid that change. So when I look at this, naturally, I want to always do something horizontally, because notice left to right relationship, no matter where we are inside this shaded area, the right curve is always f and the left curve is always g. So I want to maintain this. I want to do a right to left relationship. So now we just have to decide how we're going to do this. So we're going to rotate this about the x-axis. So if we are rotating it about the x-axis, we have a horizontal rotation, and our right to left relationship, our relationship is parallel to the axis of rotation. So we have horizontal lines, and we're rotating it horizontally. That's screaming at us to use shells, because if we look at that guy right here, and we imagine we take one of those little thin rectangles and we rotate it, it's going to give us this tin can. And we're going to have an infinite series of nesting tin cans. So that's screaming at us to use shells. All right. If we wanted to use washers, this would get very messy. We're rotating it about the x-axis. We'd have to use a top to bottom relationship, and would have to use and integrate this into 2 pieces, because to the left of 1, we have a different top to bottom relationship than we do to the right of 1. So this is screaming at us to use shells. But if we're integrating horizontally, if we're rotating horizontally, we're going to use horizontal lines. Our horizontal lines range from 0 to 2, but that's our y values are ranging 0 to 2. We need to integrate with respect to y. Anytime you have horizontal lines, you're integrating with respect to y. If you have vertical lines, you're integrating with respect to x. So integrate with respect to y. So we have to take this curve, y equals the square root of 4 minus x. We have to solve it for x to get x in terms of y. So this is y squared equals 4 minus x. I'm going to add x and I'm going to subtract y squared. So x is equal to 4 minus y squared, right? And then if I look at y equals the square root of 4 minus 4x, then y squared equals 4 minus 4x, or 4x equals 4 minus y squared. Divide by 4, x equals 1 minus 1/4 y squared. Right, so now I'm going to set this up. My volume, I'm going to go from, my y's are going from 0 to 2. Oh, I should have put that 2 pi outside, but I didn't leave myself enough room, right? So now the radius of one of these things, well, it's really nice. When we're rotating along an axis, the radius of a cylindrical shell is either x or y, depending upon we're rotating horizontally or vertically. If I go from my axis of rotation up to the outside of the can, the length of that line is always going to depend on y here. So it's y. And then it's going to be my right function minus my left. Always right minus left. So it's the top of the can minus the bottom of the can. So the right function is 4 minus y squared minus 1 minus 1/4 y squared. You can integrate with respect to y. Right, and I'm going to clean that up. I'm going to pull my 2 pi out. That makes me feel better. 0 to 2y. And I get 4 minus 1, which is 3. And negative y squared plus 1/4 y squared is going to be minus 3/4 y squared dy. So that's how we would set up the integral. I would just distribute this. This is just 3y minus 3/4 y cubed. And there you go. All right, so here's my little table. If you have a horizontal rotation, so you're rotating horizontally, and you have a nice top to bottom relationship, then you use discs and washers and you integrate with respect to x. If you're doing a horizontal relationship, but you have a better right to left relationship between your curves, then you're going to use shells and you can integrate with respect to y. If we're rotating vertically this way, right? And we have a better right to left rotation, then we're going to use discs and washers and integrate with respect to y. If we have a better top to bottom rotation and we're rotating vertically, then we're going to use shells, and our integration variable would be x. Always remember, in your integrals, outer minus inner, top minus bottom, right minus left. If the area is flush against the axis of rotation, there is no inners in discs. If the area is not flush against the axis of rotation, we use washers. We take the pi out. It's the outer radius squared minus the inner radius squared. Shells. It's always 2 pi, the radius, the top minus the bottom. If we're integrating with respect to x, that would be a horizontal rotation. Nope, sorry, vertical rotation. I was doing it right. I wasn't saying it right. Vertical rotation. If we're doing a horizontal rotation, it'd be right minus left, and we'd integrate with respect to y. All right, so I'm going to set up 4 more integrals and leave the integration up to you, okay? And verify that they come out the same. That's the challenging part, right? So let's consider this area bounded by the functions 1/4 x cubed and 1/2 x squared. Which is which? Well, if I put 1 in into this first one, I get 1/4, and if I put 1 in here, I get 1/2. I get 1/2. So I know that this must be 1/4 x cubed, and then the one on top must be 1/2 x squared. Right? So this is really kind of nice because we can do either top to bottom or we can do right to left. This lends itself nicely either way, but we're going to set up all 4 scenarios. We're going to rotate about the x-axis, the y-axis. We're going to use shells and washers, okay? So I'll slide this guy up. And let's say set up for each of the situations. All right, so we're going to do washers, and we're going to rotate about the x-axis. Oops, sorry, I didn't mean to knock my camera. So we're going to rotate about the x-axis, and we're going to use washers. So when we use washers, we're going perpendicular to the axis of rotation. So washers would be this way. So we're going, I can see that it goes from 0 to 2, and it goes up to 2. So you can verify that the points of intersection are 0, 0, and 2, 2. So using washers, my volume is going to be, well, if I'm using washers, I'm using vertical lines, so my integration variable is x. X ranges from 0 to 2, right? I have my pi, and then it's going to be my top radius, or my out, because this is my axis of rotation, so this is my top line, that's my inner line. So my top function is the 1/2 x squared, so it's my outer radius squared, minus my inner radius squared, 1/4 x cubed squared. We're going to integrate with respect to x. If we were to use shells, well, here's where things get a little interesting, because if we're using shells, we're now going right to left, right? So I have to now turn these equations into equations with respect to y. So I'm actually going to go back to this page, and I'm going to do x in terms of y. So if y equals 1/2 x squared, then 2y equals x squared. And this is where you have to be super careful, right? Because if I take the square root of both sides, the square root of x squared is either positive or negative square root of 2y. So we have to decide, is this the positive or the negative square root of 2y? Well, notice x always will be positive because it ranges from 0 to 2. So x has to be positive, and x is equal to the square root of 2y. If this part of the graph, if we were looking at this piece over here, then x would equal negative square root of 2y. Right, so that's that function in terms of x. And then y equals 1/4 x cubed is equivalent to 4. Y equals x cubed. We're going to cube root both sides. And cube root of x cubed. We get x is equal to the cube root of 4y. Now, right away, I really rather integrate with respect to x because I don't like using radicals in integration, especially when they're not nice radicals, but that's right, we're only setting it up anyway. So here, notice I didn't do the plus or minus because cube roots, anytime you're taking an odd root, there's not that plus minus option. So if we were to use shells here, my volume would be, I'll take it out, I'll remember to take it out this time. All right, we're going to integrate with respect to y because all my horizontal lines are going to change in terms of y. So it's going to be 2 pi. Now the radius of any of these guys, because we're spinning around an axis, is just going to be y. And then it's going to be the right function, which is the cube root of 4y minus the left function, which would be the square root of 2y dy. And when you integrate these, I got 16 over 35 for both of them. So see if you can integrate both of those, pi, don't lose the pi, and see if you can integrate them and get the same result. Because the only way you get good at integrating is by doing lots of integrals. All right, let's take the same area and rotate it about the y-axis. So we're going to use washers and we're going to use shells. So this time if we're using washers, we're going to go left to right. We're spinning it this way. All right, and I'll refer to that picture up above because I probably made that a little too small. So using washers, it's going to be pi. Y still goes from 0 to 2. Okay, but it's going to now be my outer radius. So my outer radius would be the length of this line. My inner radius would be the end of that line. And notice I'm integrating, I've got little horizontal lines, so I'm going to be integrating with respect to y. So it's going to be cube root of 4y, my outer radius squared, minus my inner radius squared. Okay. If we were to find this area, but use shells, we're going to go top to bottom, and we're going to spin this guy right here. That would be my shell. My volume would be 2 pi, x ranges from 0 to 2. And because we're spinning around the y-axis, the radius is just x. The top function would be the 1/2 x squared minus the bottom function, which is going to determine the height, which was 1/4 x cubed. And reintegrate with respect to x. I'm not sure which one you want to integrate. Both of them work out nicely. And when you integrate them, I got 4 pi over 5. So I challenge you to integrate those and see if you can get the same result. All right, so lots of practice, set up lots of integrals, and hope to see you zoom in with some questions. Have fun.